Dear students, welcome to the first theory lecture in robotics. I tried now multiple versions of the recordings, including iPad and so on. This was the best, as I hope you can read things on the board. I really need a board to explain things, and writing it on an iPad was just resulting in very random lines generated on the screen. So let's try it this way and see if this is an acceptable quality. So today's lecture is really bringing us on the right way to abstract the structure of the robot to some mathematical equation, which will allow us later to do analysis of how to improve cut to correct errors and how to stabilize the robot in a path. So what we will be looking at is some manipulator, usually a 2D robot for the whiteboard. In general case, of course, it's a 3D structure in the world. What we discuss here applies to mobile robots as well, but we are using manipulators as examples just because of the higher, because they have usually more degrees of freedom than a regular mobile robot. A mobile robot has just maybe 3 degrees of freedom, 2 translation, 1 rotation. The manipulator has, in general case, 6 degrees of freedom. So we have a lot more parameters to deal with. And such a manipulator has, in our case here, 2 rotational joints, which create a rotation by an angle θ1 along this axis, sticking out of the board, and a rotation around this axis, sticking out of the board via the angle θ2. And what we are interested in doing is to understand how to execute a task which requires the robot to move on some predefined path here through the environment. With what we are trying to understand is which angles do we need to adjust on the joints to keep the robot on the path. And later, we will also want to know what torques or forces the motors need to apply on the axis to keep the robot on the path. So I apologize if I disappear sometimes from the view, but I just wanted to have the board as big as possible in the camera image. So before we get the relation between the torques and the dynamic state of the robot, let's just step one step back and try to understand where the point PW is, which is the position of the wrist in the workspace of the robot, while being observed in some world coordinate frame 0, in which usually the task is defined. So the red coordinate frame is a coordinate frame in which the system executes the task, and we specify a path through the environment expressed in this red coordinate frame, defining the green path or later trajectory. And to do this, we need to find a function which calculates the position of the wrist in the coordinate frame 0 of the task. So we note that we will be always writing in the top left index, which is the frame in which the vector is defined. In this case, the vector PW. The vector PW is just a connecting vector between the origin of the coordinate frame and the point which we are observing. And we would like to know basically which joint orientations we need to adjust on the robot to let the answer vector be a PW. And this function is not just one function. Since we, in the two-dimensional case, we have to calculate the xy position, you see that there is a function taking the θ1, θ2 orientations to calculate x, and there is a second function, f2, so you can say it's an f1 theta and an f2 theta, which is basically calculating so the function f, which we see here, is commonly called the forward kinematics of the robot system. And we would like to find a method which is the easiest way of finding this function given a robot structure. So to do that, in such a robot frame, we need to identify first what are the moving parts of the robot. So we will need to assign additional coordinate frames to our system, which are attached to independently moving parts. So we see, since the world is usually resting, this is the table on which the robot is mounted. We have a second coordinate frame, x, y coordinate frame 1, which is attached to the first link. We will have another coordinate frame. This is the coordinate frame 2, which is attached to the second link. And usually for convenience, we will also attach the coordinate frame of the wrist to the answer vector. These two, I'm saying for convenience, just because there is a rigid connection between the last two usually. It's just for us to simplify the calculation. And each of the frames, basically now, specifies the motion of the robot through the space. So in general case, we don't have two-dimensional systems, but three-dimensional systems. And we need to, let me see if I can switch it here. What we also can see here is that I defined the point PW as just position xy. As you see on the slide, I hope you can see it. We have two definitions of the workspace. The primary workspace is just dealing with reachability. That means it's an XY Z representation in which I can reach some point in the environment without considering about from which direction I am actually approaching some point. And the secondary workspace, as defined on the slide, adds to the information also the orientation. So if I have some square object that I want to grasp, it makes sense, for example, to approach it from this direction, which has some orientation alpha, let's say, to the vertical. It does not make sense to approach it from this direction just because it's not aligning with the surfaces I want to grasp. That's why the secondary workspace takes also the orientation of the points into account. In this case, I need to extend my point representation. So my point in the secondary workspace would have, for this two-dimensional robot, an X and Y and an alpha, an orientation, how I approach it. So this is something which we will try to analyze and to calculate for our robot, given θ1, θ2, knowing also the length of my robot. So what I also know is how long is the first link and how long is the second link, to calculate basically the position in space. To do this, we will look at possible degrees of freedom which exist between the different coordinate frames. And in general, the origin, for example, of the first coordinate frame relative to the 0, 1 can have some translation in X, Y, Z, can have some, so the origin can be placed in general anywhere in the 3D space. And while the while the robot is moving around, we will have also some rotational parameters added to it, describing the additional degrees of freedom of rotation. What we will assume is that each of the coordinate frames is a right-handed system, X, Y, Z. X right-handed just because if I take the thumb and point it towards X, then Y is pointing towards my pointing finger, and Z is pointing towards my middle finger. That's what we have to use right hand for this. Some don't use the left one. Some people are writing with the right and checking the coordinates with the left. Usually this results in the wrong answer to the question. So right-handed system describes basically a position of the coordinate frame in the parameter space of the previous one. And some point where the origin is placed can be now expressed with X, Y, Z. Orthogonal has the advantage that if I move the point along, for example, D, it does not change an XY position. Also, if I shift the position along X, the YZ position doesn't change. So we have a decoupling of influence of the parameters. So what we are using are always orthogonal right-handed systems to describe the translation space. Now, how do we describe the rotation? Okay. The rotation is usually a rotation around some rotation vector. And the rotation happens here, for example, by some delta P. So the rotation will be also represented by a vector. The vector direction is basically the orientation of the axis around which the rotation happens. And the length of the axis is basically represented by the angle of rotation. And for convenience, we could, for example, use here the 3 rotations around X, Y, and Z. I call the rotational angle alpha, beta, gamma here as the missing 3 degrees of freedom of the robot in the orientation. So what we will be getting from the system is basically 6. What we will require the pose being position and orientation of the anti-vector be defined by, in general case, is by 6 parameters, 3 of them describing the translation in the right-handed coordinate frame, and 3 of them describing the rotation as 3 angles, which needs to be specified. So this basically represents the rotations. How do I understand rotations in such a system? Let me erase the board first. Let us take these 2 coordinate frames. So what usually happens is we have our original coordinate frame represented by the head on X says that this is a vector along the direction of the x-axis of the 0 frame. Here we have the vector representing the direction of the y-coordinate. And what can happen is, of course, in a 2-dimensional case, is that the first vector will be rotated by some angle alpha, which will give us an x1 and a y1, being the corresponding directions of the x and y axis after rotating by angle alpha. So now, if I take some point representation P, the vector from the origin, and I may know the coordinates of the vector P. You remember from high school, I hope, that the coordinates, if I want to express the coordinates of the vector P in the 0 frame, then I need to project the P vector with a scalar product onto the corresponding vector. And this gives me the x coordinate in the 0 frame. The inner product or scalar product, like if I'm projecting 2 vectors on each other, v1, v2, then the scalar product is just v1 transpose times v2, and the resulting the result of this inner product is a scalar, which is the product of the length of v1 multiplied by the length of v2. This is the definition of scalar product. If one of my vectors is, for example, the unit vector of the coordinate frame, then the corresponding norm will become 1, and this will become a length along the vector. So this scalar product here is telling me how far do I need to go along x0 to reach point P, and how long to, and the other scalar product here, sorry, y0 in 0 transpose P gives me the corresponding y coordinate. So we see that this definition is basically telling me what are the xy coordinates in some specific point frame 0. Now, to get the point representation now in the new coordinate frame 1, what I'm interested in is now, oh, sorry, the wrong color, is to project the P onto x1 and onto y1. We see that the coordinates will be completely different. The length of the vector will be preserved, but the coordinates will change. And this is nothing else but a scalar product of x1, p0, and scalar transposed, and a scalar product of the unit vector towards the new y1 transpose times p0. Well, the scalar product needs to be executed in vectors which are represented in the same space. That means I need to represent the direction of the x1 in the coordinates of my original vector of my original coordinate in 0. So what is, for example, x1 in 0? We see if this is a unit vector, it's the length 1. This is a 90-degree angle. So the x component of x1 is just cosine of alpha. If alpha is 0, the entire vector becomes 1 and they align. If alpha is 90 degrees, I will have no contribution along the x0. So this is basically how do I express the direction of x1 observed in the 0 frame, and the corresponding y coordinate is sine alpha. So this is the first vector. From here, what's my y1? What's the direction of a y1 vector expressed in the 0 frame? What's the x direction? So alpha is also here, and these are my 90 degrees. So we see that the x direction, this component, is just minus sine alpha, just because this length is 1, and the corresponding y component projected on the space is just cosine alpha. So now I can write this equation here again. It's basically P in 1 is equal to, now I pull the P0 out of the bracket, since it applies to both. And what stays is on the top, the transpose of a vector is just flipping lines with columns. So if the origin was a column vector, this will become a line vector. I will write for cosine C alpha as abbreviation, and I will write for sine S alpha. And from the other one, it's also written as a line vector. will become S alpha. And this is called an elementary rotation matrix. By an angle. So this, we can write this matrix also as a 3D matrix. So P1, we see that this matrix rotates around the axis sticking out of the board, around the Z. So the P1 matrix extended now to a 3D system will be 0, 0, 1, 0, 0, cosine alpha, sine alpha, minus sine alpha, cosine alpha times P0. So this is basically the transformation which rotates the representation of the point from the first frame to the second frame, which may be rotated due to changing the orientation by θ1. Now we have one more problem here. If you look later in the book, this becomes plus, this becomes minus. Why? Because the alpha usually is understood as not as a rotation of the coordinate plane, but as a rotation of the observed point. So I can rotate the point by 10 degrees. Then it moves from here to here. So this would be a positive rotation around the vertical axis. Or I can rotate my coordinate plane by 10 degrees in a negative direction and get the same result. If I plug in minus in the black one, so cosine plus or minus is the same, so that's why it says cosine. Sine of a negative value is minus sine. Same is here, so the two minuses give the plus. So that's why the rotation around Z, the elementary rotation around Z, is basically something which does not change the Z coordinate, and it's having the cosine and sine expression like this. The same is true for some rotation P2. If I try to rotate around the x-axis, I get 1, 0, 0, 0, 0. And now this elementary rotation matrix, cosine gamma minus sine gamma, cosine gamma. This is basically times P0. This would be a rotation around an x-axis, also Rx. And the last one, give me a second. The last elementary rotation matrix would be, of course, rotating around y. So the y coordinate stays preserved. Here I have also the cosine beta in the diagonal. For the y, you need to remember that the sign changes. So the y coordinate has a plus sign beta here and minus sign beta here. If you draw it the way I did in my image for y, you will see that this makes sense. So this is basically the elementary rotation matrix around y. And this gives us a point in some third coordinate frame, which is undergoing a rotation just by applying it to the original point P. So now we see that the rotation matrix, again, let me just erase, this will be an entertainment now with erasing. We can now understand that if I have some point in the link 0 and I'm applying a rotation to it to be a point in frame 1, we just defined that the orientation could be explained as a sequence of rotation around x, around y, and around z, applied to a point 0. You could understand it as first we do the matrix operation will be applied on the vector from the left. So first we would do rotation around x. Then we will apply rotation around y. And then we will apply a rotation around z. So that means this product here corresponds to the rotation matrix R. And this is one way how to actually calculate, have to derive the free rotation angles from the rotation matrix. We get this 3 by 3 matrix. And now we have this original frame, which is x, y, z. We rotate it around x. That means we get a new y vector, y prime. We get a new z vector, z prime. I have it as an animation on my slides, but VBB does not allow animations. So welcome to the tools provided by the department. So this would be the rotation by some angle alpha around x. This is the first rotation which gets applied. Now the next y we are applying is not really the original y. You need to remember it. The y this system is rotating around is the resulting y. So I am rotating around actually this y prime. And now I rotate basically the x and the z. This will be an x2 dot and the z2 dot rotated around the corresponding y vector. And the resulting z rotation is not the rotation around the original z here, but it's around the resulting z parameter after applying the rotation twice. But still, this gives us a way how to decompose the 3 by 3 matrix coming from some sensor navigation system into the 3 alpha, beta, gamma angles defining orientations around the axis. So this is actually what's also happening or not happening. Here, this is actually an animated version of what I was trying to show here, showing basically how this evolution between the original one, the second one, the third one, and the resulting one. So the second is basically the sequence of rotation around x, y, and z. And the resulting coordinate plane is the blue one here in the image. This is interesting. Let me just stop for a second. Or not. Need to check what happens. I need to check what happens to the slide, but I actually added now the right one, which is also in your handout. So my rotation matrix could be now understood as a sequence of this elementary x, elementary y, and elementary z rotations. And you see here on the screen the 3 rotation matrices which are associated with them. So this is the rotation around x, This is the rotation around y and the rotation around z. And if we multiply them all together, then we see that the alpha, beta, gamma angles, which express rotations around x, y, and z, result in product terms like the one here on the screen. And this product representation would allows us to recover the three, we call them Euler angles. So we see the first one. So you need to understand that each element of this matrix is basically kind of RR element. So this is RR1, this is R12, R13, R21, R22, R23, R31, and so on. So now if you look at what's R11 square plus R21 square, it's cosine alpha, cosine beta, cosine alpha, cosine beta, square. So this is R11 square. And the second term is R21 square is sine alpha cosine beta squared. This is basically the R21 square. We can pull the cosine beta outside of the bracket and write, I hope you can see, cosine alpha square plus sine alpha square cosine square beta. And now, knowing trigonometrical identities, cosine square of an angle plus sine square of an angle is 1. It means the whole thing in the square root becomes cosine square beta. And if I take the square root, on the bottom I get cosine beta. And the other angle is R31 with minus. 31 is this one here, and minus, it becomes plus sine beta. So I get sine beta here. And I see if I take an inverse tangent, this gives me the beta. So taking the minus R21 in the numerator, dividing by square root of these two, gives me an arcus tangent expression here. The problem we are having here is that the arcus tangent is defined, the tangent function is defined just between plus 90 degrees and minus 90 degrees. So if I would just take the arcus tangent itself, the result will be just 180 degrees. There is an arcus tangent 2 function, which is on the next slide here. Let me just switch to it. So we see that the arcus tangent 2 function extends the response to full 360 degrees just by analyzing in which quadrant we are operating. So if the denominator is bigger than 0, then we are in the positive part of the coordinate frames, in the x positive. That means we want an angle between minus 90 and plus 90, and this is exactly the value of the original tangent function. That's why we can use the arcus tangent. If we're in the negative axis, negative x, then we just add to the result pi. So we add 180 degrees to the result of the tangent, which extends it now to the values of the remaining 360. So in the end, the acostangent function gives us as a result directly an angle between 0 and 360 degrees, taking correctly into just by analyzing the numerator and the denominator. That's why we plug into the function not the result of the division, but as you can see, just a second. As you sorry, I didn't have the microphone on, so let me try this again. So as we see here, now using the acostangent 2 function, if we plug in minus r p1, then we have the sine typical expression, and this gives us a cosine beta expression. After what we plug in here is, of course, our numerical values. The matrix in reality are just 9 float values, which we use to do the calculations here. And from these 3 float values, using the acostangent 2 function, we get the beta. Once we have beta, we can calculate also the alpha angle. We see that, for example, if we divide by cosine beta, the beta value is already known, these 2 arguments, then we have a cosine alpha, sine alpha. Now using the same acostangent 2 expression, gives us a 0 to 360 degrees value for alpha. So just by looking at the correct elements of the multiplication here, we can try to extract the numerical value of the so-called Euler angles of this representation. And the last one is gamma in the same way. So we see that the 2 other parameters basically require a division by the beta result, the cosine of the beta result. And this brings us a problem. It's called Gimbel lock, or singularity of this Euler representation. So if for beta equals to 90 or beta equals to minus 90, the division here is by 0, and the division by 0 is not allowed. That's why for these special cases, for the singularities of the representation, we need to predefine what alpha is. In this case, alpha is assumed 0. And the gamma can be now derived from a simpler version of it. It's basically taking the 3-2. Let's see. It's taking basically values. So since we have alpha 0 and beta 90, many of these terms simplify to 0, and we get a more convenient way of calculating gamma. So the alpha, beta, gamma are just our interpretation of the rotation. So the rotation is actually something which describes rotation around the axis. So what happens in the work is that we have some rotation axis, and there is some rotation by an angle delta theta happening around this axis, and we are explaining this rotation by some arbitrary coordinate plane, which was defined by our task. That's why we are also getting this singularities here, because the axis around which we rock, we explain the rotations, do not correspond to the axis of the rotation. We can work around it just by, let me just switch, just by using a different explanation of the rotation. So here we see that we explain the rotation matrix not as x, z, x rotation, but in this case we explain it as x, z, x rotation, which is also a proper angle representation. You can look it up, for example, in Wikipedia. And multiplying now the three elementary rotation matrix around x, around z, and around x again, give us this product in the matrix. The index here is basically the number of the angles. So you see S3 here means sine of the third angle here, and S1 is sine of the first angle, of the x1 angle. So we will be using these abbreviations all the time. We will not write sine cosine, but we will write C and S. And we see that we can choose now different products, which still are proper explanations of the rotations, but all of them actually just define some arbitrary axes, which have the singularities of different positions. So now, if your robot passes through beta equals to 90, then the original x, y, z analysis of the rotation matrix would require you to do singularity checks all the time while decomposing the matrix. But you may choose maybe one of these if you have limited ranges of the angles to find a better explanation of what's happening. But in the end, there is always some singularity which you need to deal with. That's why there is a different way of explaining the rotation in space, and this is the axial angle representation, which I started explaining already here before. So for the exam, we will use to derive this axial angle representation. But I will just to show you once where it comes from. So basically how this K, which is axis of rotation, corresponds to, what is it called, capital X and lower x. So what is the capital X? Vector, some small x vector, which explains the rotation in some coordinate frame between 2 points. And now basically what you see, what's happening here is that to get to the small point x, what we can do is we can go along the vector k. This is basically the vector along which we are moving. And we walk along the magnitude. This is a different way of writing the scalar product. I was writing it as x transpose times x. This bold dot represents in this case also a scalar multiplication. So the scalar multiplication x scalar k, k being the unit vector, gives us how far along k I need to go to reach this disk here. So this brings us to the center of the disk. And now x minus this. So the x vector, if I go minus vector here, so minus this previously calculated value, plus x, this expression is really just this vector in the rotation plane. So this is the first vector, and the orthogonal vector to this is basically if I take the vector k and I build a vector product, so the cross here is a vector product between k and x. So I have here a plane spanned by x, spanned by k, and the vector product is calculating a vector which is orthogonal on the previous two. This is how the vector product is designed. And this is basically now this value here, an orthogonal vector. And so I define for this, I define for a vector here, and now I need another vector, intermediate vector, which is orthogonal to it. Why do I need it? Just because if I locate the point by P, I need to express it in the polar coordinates of this local coordinate frame. So you see you have a cosine and sine expression defined in the xy coordinate frame of this. So now if I draw this list here, and this is my x minus x k times k. This is the first vector, and the second vector is k cross x. These two are orthogonal. This is my original point, which is for cosine equals to 0. If I have that cosine equals to 45, for example, this is basically just now this vector. This vector just by cosine the angle. This is basically this first expression here, plus this way, plus this value along this vector, and this is basically just this times sine theta. So you see that this is a complicated expression explaining just the point axis rotation. Again, you don't need to derive it. It's just to show you where things are going. And now the problem we are having here is, on one hand, that we have a cross product here, a vector product, vector product. What we would like to have is just products and sums of matrices, and not some scalar or vector product of vectors, just because we would like to decompose the R matrix into some sequence of matrix operations. So the first thing we do is we look at ways how to change the vector product. So what we have in our notation is k cross x, which is basically kx, ky, z, the three coordinates of the k vector, cross product x, y, z. These are the three vectors of the second product. So we calculate what happens here. So the first one is kyz minus kz y. The second one, the second entry is kz x minus kz z. And the third one is kx y minus 3y x. This is just applying the rule of the vector product calculation. And now I want to write it as a matrix times x, y, z. I would like to replace the cross product with the matrix multiplication. And now in this equation there is no x, so there is 0 in the x element. It's a minus kz as one of the elements showing up here. And we have ky times z. So this is the first line. The second line, there is a kz times x. There is no y, so the y component is 0. And there is 3x times z minus. And in the first line, it's minus ky x plus kx. And there is no kz. And this skew matrix K, so I can write K plus x is equal to multiplying x with the skew matrix built out of the elements of my original vector, and this gets rid for me of the vector product. And we see this is an antisymmetric matrix, so the skew matrix with zeros along the main diagonal. So now we can write the whole equation. What changes, it was originally here k cross x. Now we have this k skew matrix times x times sine. And the other stuff is really now just grouping things together using existing rules for identities in trigonometrical identities. So I will not go through. So if there is a problem, we can discuss it in an online tutorial on Monday. But this just shows you basically, no, the next one, how the whole thing gets simplifies to something where the original x. So we see that at the beginning, the resulting x, the result of some complex product, and the inner product, vector product of values. What we know that what's happening is it's just a rotation. What's happening is there is just a rotation happening between point capital X and point lowercase x. That's why we need to simplify this complex structures here to something which just basically is x equal to, and you see here, I'm start having exactly what I wanted, just expression with x, with matrices and some scalars multiplying the matrices. So in the end, if I group them all together, I see that the rotation matrix can be interpreted as identity. I is the identity matrix plus 1 minus cosine theta. This comes from this grouping of the sine cosine expressions here, times k square. So this is the skew matrix built from the direction vector multiplied by itself, moved itself, and sine theta multiplied with the skew matrix. So this is, and the Rodriguez formula allows us now to recover the theta, we see that we can R minus R transpose. This gives us basically just a non-diagonal matrix. So let's just maybe, before we explain the last step, look back at the properties of the rotation matrix. What we noticed while decomposing the rotation matrix into the elementary matrices is that the rotation matrix is the direction vector of the closed system expressed in the original one transpose, and then the y direction vector transpose in 0, and then the z direction 1, 0 transpose. It means any line. So if I call it basically some vector 1 transpose and vector 2 transpose and vector 3 transpose, the length of each of the vectors is 1, just because these are the unit direction vectors, showing us the orientation of the axis. We know also that dx transpose dy equal to 0 if x is not equal to y. So if I take the two vectors, line column vectors from the matrix, then they are always orthogonal, and the scalar product of them becomes 0. And the determinant of R equal to +1. Why is it important? You see that a vector gets multiplied by this matrix to get the new vector, and what the system is supposed to do is just a pure rotation. So it should not change the length of the vector, it just change the orientation of the vector in the new coordinate frame. If the determinant of the system of the rotation matrix were not 1, then the vector would be stretching or squeezing the vector. If the determinant is 1, it means that the length will be preserved, but just the direction is changed. So now, what we also know is that rotation, I will not prove it, but it's very simple to do it just by using the knowledge that all the vectors are corresponding direction vectors. So the inverse matrix of the rotation matrix equal to transpose. So it goes from capital X to small x. So small x to capital X, so the other way. Then I need to use the inverse matrix to do that. And in case of a rotation matrix, the inverse is easy found just because I need just to transpose the elements. Transposing elements means the line vectors become now the column vectors. The transpose to this one R transpose would be x1 y1, so y1 and z1. So you see whatever the lines here become column here, and this is also the inverse. And I leave it up to you to prove that these two multiplied together is 1. You can see that the first element is this vector and this vector becomes 1. And all the other elements are orthogonal, so if I multiply this with any other, it becomes 0, 0. Only the diagonal elements become 1. And this is kind of simple proof that the transpose and the inverse are the same. So the property of the matrix is that the inverse is equal to the transpose. Now, if you look at this expression here, R minus R transpose, what's happening here is I am subtracting from a matrix A, B, C, D, E, F, G, H, I, subtracting A, B, C, D, E, F, G, H, I. As you can see, the diagonal elements in both cases are same, so I get 0 values here, and here I get basically B minus B and so on. So I get non-zero elements here, and this is a skew matrix. That's why you see R minus RT gives us already the elements of the vector. So now if I would take these values, so this is my K skew, and from this I can build my K, just by taking this numerical element and putting it with minus as a Z component. So this minus B minus B, and this would be my Z element of the corresponding vector, and correspondingly I would pick now this value, that is my Ky. I will pick this value and this will be my Kx. So you see that from this R minus RT, I can reconstruct my K. The problem is that this vector is not a unit vector. So if I normalize it, then the norm will be equal to 2 times. So this is a K prime. If I normalize the K prime, this will be equal to 2 sine theta. If I divide it by 2 and take an arc sine, an inverse sine, then I get directly my theta vector from this expression, and I get also my K at the same time, just by normalizing by the calculated sign. So we see that going through this complex sequence of transformations, we find an explanation which which assigns to the 9 elements of the rotation matrix now an explanation which involves an explanation having it as a rotation matrix, as a rotational vector and a rotation theta. Why is it important? It's important because this is the natural way how the rotation happens in space. And this representation has no singularities. And this representation is exactly the axis angle representation is exactly what we will be using later in our Jacobian representation of the robot. So just remember this. Remember that from the rotation matrix, you can always recover these elements just the way I just explained. So here we have exactly this axis angle representation, and usually the axis angle representation is very difficult to use in operation. So if you want to add angles, add rotation to the other. So a sequence of rotation as a matrix representation is just applying the rotation from left. So I can, if I have 3 rotations, you've seen it already with the elementary matrices, I just multiply from left the sequence of rotations, and the sequence is always from right to left. And this gives me the final rotation. I can also multiply the entire product of these 3 matrices and use them as an intermediate result to deal with the rotation. For axis angle, it's difficult. That's why people use quaternions. And you see that there is a natural relation between quaternions and this axis angle representation. The angle theta in the quaternions has 4 elements. The first element is just cosine of the half of the angle of rotation. The second element is the x component of the rotational matrix times sine of the half of the angle, then y sine of the half of the angle, and z. So similar representation to what we just derived. Then the nice advantage is that it does not have any singularities. So advantage of the quaternion representation is it's compact. It does not have any singularities. And just get it too blind. And it naturally reflects what's happening in space. So our system really, this is exactly what's happening because of the rotation on the axis. Our explanation with some arbitrarily chosen angles is just not the right way to go. Let me just see. So what's the configuration space of the robot now? So now we know basically the degrees of freedom. We know that we have 3 translations of our configuration of the robot. Our configuration of a point, an object in space, consists of its translation parameters, x, y, and z. And if we use the Euler representation, it could be a sequence of 3 Euler angles, alpha, beta, and gamma. If we use an axis representation, then our Q becomes x, y, z, and theta times kz. And 3 elements of the rotational axis, x element, y element, and z element, multiplied with theta. We can derive now, we can extract now the direction by writing it as a 3-dimensional vector and normalizing it. And the amount of how far it's rotated, it's basically just the length of the corresponding vector. So the configuration of a moving object is a specification of every point on the system. So I have a rigid box. Then this represents basically the motion, the position of one point, and it's a rigid point, of course, defining one point on the object defines all position of all the objects because there is a rigid relation between this point and everything else on rigid. This is also true for the robot. So we have a robot. Then, if we know configuration of one point on the one, then since it's rigid, it defines also the position of all the other points of the link one. And if we know position of one point on link two, then we know the position. So specifying the motion property of some point here, and the motion is generated by theta 1, defines completely how the first link is moving, and specifying some motion of point just by changing theta 2 specifies also all other points on this link, just because all other points are usually connected to this. That's why our configuration space completely for this rigid robot with 2 rotational links is completely captured by the current orientation of theta 1, theta 2. So the configuration of a free-floating object is defined by the 6 parameters of free motion. The configuration of a manipulator is defined by the motors generating motions of the robot, which are usually the joint parameters. In case of a rotational or revolving joint, or it can be a translation if we have this telescopic joint which slides in and out like a. So configuration space defines basically now all possible configurations of the system. So now, how do we find the representation of the robot in such configuration space? Well, it's pretty easy. The structure, the geometric structure here on the left side corresponds to a point which takes the θ1 reading from this joint. This is basically the currently generated motion state, position state of the robot. And the other coordinate is basically taken from the orientation of the second joint. And our configuration of the two. And this is just the point. And now, as you see, this is basically what you see here on the slide. The problem is, of course, how to represent obstacles here in the environment. This is not an easy procedure. This is something we talked about in the summer class because it's a very complex way. The shape of this configuration space obstacle is a sum of the geometry of the robot and the geometry of the obstacle. You don't need to worry about this. This is how we would actually represent now this task space of the robot in the configuration space. And now planning is basically moving this point like robot to this configuration space without intersecting any occupied spaces. This is basically, as I said, not part of this, but I wanted to show you that the configuration which we just derived is also used in the planning to simplify the representation of the robot. So what's the dimension of the configuration space? It should be the minimum number of degrees of freedom required to represent something. Why is it the case? Let me just stop it for a second and erase the board. So why do we need to choose the minimum number of parameters describing the motion? Well, a simple reason is I take this type of manipulator with θ1 and θ2. Then, since it's a rigid robot, the motion of all these points can be defined by this one motion parameter θ1. And the second independent motion orthogonal since independent, called the two change relative to the one. We have already a two-dimensional system, allow space to be analyzed. If we add another piece, if we add here the first link, just to have a robot which is capable of controlling not only the position where it reaches, but also the orientation on the reach. This can be done only with 3 degrees of freedom, each of them is covering one of these parameters. Then we get this word, and now finally we become volume. As you will see, for planning, basically you try to keep the volume that you analyze to a minimum, because you just comprise the entire space into very small boxes. You have 1,000 by 1,000 in each dimension, you will have 1 billion such voxel elements to analyze for collisions. If I add another fourth dimension to it, then I would have 1 trillion tests to do. So you see, you have to keep the dimensionality low just to make the analysis later easier. And let's just look through 4 examples. So this is the simple delta flyer with a reference point here in front. It's a 2-dimensional system. So we define the configuration of this delta flyer just by identifying the position of the point as xy. You see the q is xy. And then we define some vector on the delta flyer, and the orientation of the vector relative to some reference axis defines an orientation angle theta, which defines completely position of any point on this structure. So since we know basically how it's rotated and we know the geometry of the delta flyer, these 3 parameters can be used to describe the configuration. So this is the correct way of analyzing the configuration of this related robot. So we can have a slightly different way. We were using this. The original idea was to use orientation. The other way of doing it is just using some coordinate UV, in which each point of the delta flyer is defined. So our representation would be now x, y, and then the relative u, v position in the local coordinate plane of the delta flyer. It's a big presentation, but suddenly we have 4 elements instead of 3. What's happening is you see here on the top, the u and v are not independent parameters. If I change the orientation of u, I change also the orientation of v, and it's simply expressed with the cosine and sine of the angle. So the minimum representation of such a structure is v, and we should really make sure that we use the minimum representation. Like I had once an example where I was trying to draw a screw in the nut. So there is a thread of the screw and it's going into the nut. So what you have is the one motion parameter, the motion around x. And the second motion parameter could be theta. So you could define the configuration of the screw when it's in contact with the nut. But if you look at possible points in the configuration space, you will see that x and theta is coupled. So for a specific theta, depending on how I turn the screw, I get different depths here in the nut. So I have dependencies. So if I don't choose the minimum number of parameters, then I get a dependency between parameters, and I'm wasting basically dimensionality to represent my system. So we talked about what causes motion of the robot. So as I mentioned already before, what I'm drawing mostly in the lecture is this rotational joint, bottom left. And we have also a revolving joint and a twisting joint. It really depends how the axis, if they're in the same plane, or if it's joining out of the plane, or if the plane is preserved. So we have three different types of rotation, and we have one prismatic joint, which does not require a torque to be applied to the robot here, but in this case, there needs to be a force generated by the actuator, maybe some pressure, to move this sliding cylinder in and out of this sliding element. So we have three rotational, revolving, and twisting joints on the robot, or a linear joint. And these are the only elements which create a motion, just because we assume a rigid robot, not an flexible robot. If you look at workspaces, so if you use an example, an robot, if you look from the side, the gray area here is a possible point basically the robot can reach. So the workspace of the robot is the shaded area. If you look from the top, the robot that cannot turn 360 degrees, as you can see here. There is some limit on the angles. And this is the workspace of this specific robot here. And now, so we know now basically if we have a robot like this, if we have some base coordinate 0, if we define some new coordinate 1, and so on to define where our end effector ends up being. And without any other constraint, we are free to choose where we place the origin of the coordinate frame and which way we choose the orientations of the x, y, and z axis. So we know if we have a free choice to switch between coordinate frames, I will write the coordinate transformation equation. So if I have the point represented in the 0 frame, the point can be rotated. The rotation matrix rotates from 0 to 1. This is also the rotation notation from Craig. The top left is only the index of the cone system. If it's a rotation matrix, then the lower left one is from word to word. Now to check if your equation is correct, a matrix can be only applied on a point which has the same index on the top left. So it's maybe we have two zeros. So this transformation changes the point to the 1 representation. So this would be changing basically from this rotation of this frame to rotation of the new frame, plus change in the origin. We see that the origins are also shifted. Key origin. It's a vector. And since this transforms the point already in the representation of the first point, the origin, the transformation origin needs to be also expressed in the coordinate plane of the cone. So this gives me the representation of this point if I were looking at it from the first frame. And if I want to see how it looks like from the second frame here, or from this one, then what I need to do is take the result from the first frame, what I got here, by the rotation matrix, which explains the rotation between 1 and 2. Apply the transformation between the origins between these two vectors. And this gives me the position of the point relative to the coordinate frame of the second, and so on. So we see that in each of the transformations, we have 3 degrees of freedom in the rotation. These are the Euler angles or the axis angle representation. And we have 3 degrees of freedom in the translation, x, y, and z translation. So if we don't constrain the choice of parameters, it will be 6 parameters which we will need to define for each axis. So 3 of them will define how the orientation changes, 3 of them which defines how the. And we will see that this may be not the best way of dealing with this. Well, let's take the robot which we have here. How to calculate the forward kinematic of such a robot. So we have a base here, this is my x, this is my y. I have the first axis, which has some length 1. And my theta 1 can move the second joint on, it's supposed to be a circle, on the circle here. So the x on the circle is nothing else but L1 times, if theta is 0, then I'm here, then it's just x. With increasing theta, it goes to 90 degrees, it becomes 0. So the x component at this point of the circle is just L1 times cosine theta 1. And the other coordinate, we have it already while I was running the rotation matrix, it's sine theta 1. Relatively easy. But I have not done, I have a second link. And only this is actually defined in our finalics. This is basically now telling me where my robot ends up being. And this would be my forward kinematics calculation where my end vector is depending on the joint values. So I need to activate L2 times. Well, let's just do it a little bit here. I have first line theta 1. So if theta 2 is 0, then the orientation of this line is also theta 1. So if I say that theta 2 is 0, the theta 2 would be this angle here. Theta 2 is the angle to the stretched out arm. If theta 2 is 0, then it will be only theta 1. And in other case, the orientation of this line to this point is just theta 1 and theta 2. That means to this point, I need to add now L2 times cosine theta 1 plus theta 2 and sine theta 1. It is actually the same thing as in the origin. I'm having now just an orientation of the second joint as a result of 2 orientation changes. And you see, this would be an example of my forward kinematic function, calculating x as a function of the 2 vectors theta, knowing geometry in the system. And this is exactly what's defined here. So, the definition cosine alpha is not 1 and 2, but it's alpha and beta. It's basically finding the result. This is the result which I just show you on the board. So, but What we're having as a problem is, of course, our robot is usually three-dimensional, and to have a robot which can cope with a general motion state, we need to have 6 parameters. So I will have here 6 joint parameters with a lot of structural geometry, which is moved around by motion of the joints. That's why we need to see basically how our transformation is defined. So I have this equation on the slide right here. And if I do it in the inverse way, I could also say it's P1 minus P1 origin. This brings the vector to the other side. The inverse would be the rotation from inverse rotation from 0 to 1, which brings the rotation matrix. So we see that we can also write the whole equation in a form where the translation vector is in the same. So here the translation vector is at the go. Here the translation vector is in the coordinate frame of the origin. The problem we are getting here is that if I want to calculate, I found the transformation from the base system to the first wave, and now to plug into the second wave, I will need to apply this coordinate transformation equation again on P1. And now substituting P1, this would be R12. Now, the whole thing can be substituted like this. So it would be R01 times P0 plus R12 times P1 origin plus P2 origin. So I just basically plug in this into here. So basically, this is kind of my origin in 2 between 0 and 2. So this green, this component here corresponds to this translation vector, and is expressed in the goal train. Oops, sorry. And my original point needs to be rotated. So you see, first I rotate it from 0 to 1, and then I rotate it from 1 to 2. If I multiply the two matrices first, then I get the rotation matrix from 0 to 2. But if I want to go from frame to frame, it's a very tedious operation just to collect all the terms, make out of them translation vectors again, and so on. That's why we try to combine everything here now to one matrix. And for this to happen, so our point, the fusion point, would be x, y, z, 3 dimensions. We get homogeneous coordinates. Where a point expressed by x, y, z the scaling factor in our case is 1. So points become now 4-dimensional vectors. If it's a point, then we have a 1 here. The 1 means this vector has an origin. Point has an origin in the coordinate field. That's why we have here 1. The velocity, which is the of the point, has 0. As you can see, if you subtract 2 points, actually you get the 0 as well. The 0 on the bottom means you don't have an origin. So the translation of the origin, the translation of the origin doesn't need to be considered in the calculation of the vector. So we actually make things worse. We have now 4-dimensional vectors. How does it change our expression? So originally we have this expression P is equal to rotation P plus translation. Now we have this P homogeneous. From now on, I will skip the homogeneous. Our points will be always homogeneous in some coordinate term x. Is equal. I have my point homogeneous in 0. So I assume I have an x, y, z represented in my work frame. And now I'm trying to calculate representation in some arbitrary frame. So let's say in the first frame, it means I need to multiply the x, y, z component by the rotation matrix. So the first, instead of writing ph, I could also write here x, y, z, 1 in, let's say 0. This is a rotation from 0 to x. And you see that it will be exactly what I need. The 3 elements multiplied with the 3 elements of my vector. And now I write the P origin in x as a column vector here. So I get here a 3 by 3 matrix in the top left. I get a 1 by 3 vector. Actually, if I give you the origin, the P origin is already homogeneous coordinates. This will be x, y, z plus 1. And it's still here 0, 0, 1. So instead of writing my coordinate transformation as rotation point plus translation, I combine it all in one bigger transformation matrix. This will be a transformation matrix, which in our case transforms from 0 to x. And as you see also on the slide, the transformation matrix has some rotation component from 1 to 2. If it's from 0 to 1, it will be 0, 1. If it's 0, 2, then it will be multiplication of this and so on. So one nice thing is that now transforming my work point to the plane of the first joint, all I need to do is just to multiply it with the transformation matrix transforming from the work to the first plane. This gives me an older representation of the point in the first plane. Do I want to the representation in the second plane? I continue multiplying it now with the matrix from 1 to 2, and so on. So to get the transformation from 0 to 6, if I have 6-dimensional product, we need to get to 0, 1, 1, 2, all the way to 5, 6. Now, if the robot has a static position, I can pre-multiply this transformation matrix to one 4x4 matrix. The 4x4 matrix will also have a structure with zeros here in the last line and one here. And if you have it in the exercise in the tutorial, the resulting rotation matrix will be the product of rotations. And the corresponding translation vector will be also propagated exactly the way I've done here. So switching from Cartesian representations to homogeneous representation allows us to define basically the position of the robot by multiplying with a matrix. And now, so one way what I have 0, 1, it will be the rotation of 0, 1 origin expressing 1, 0, 0, 0, 1. This is my transformation matrix. And if you remember that the inverse I had just before was R0, 1 inverse times P1 minus P origin P1, which can be written as rotation 0, 1 inverse P1 minus rotation 0, 1 P1 inverse origin. So if I know the representation of my transformation matrix to go from 0 to 1, and I want to go in the other directions, I would like to transform. I know the representation of the point in the 6th coordinate frame. I know P6. And I will the point is in my 1 frame, then I will multiply the inverse matrix going from 6 to 0. Similar to what I did here. If I know from 0 to 1, how do I build the inverse from 1 to 0? Well, it's actually already here. You see that I need to get the inverse matrix 1, 0, 1 inverse. My translation vector will be now minus R 0, 1 inverse times P of origin. So to calculate an inverse from the inverse rules, I know what the last line will be 0, 0, 0, 1. What else happens here? Well, we just discussed the properties of the rotation matrix. The inverse of the matrix is just the transpose. I need to find the elements here. I just need to switch the lines and columns here to here, whatever works, and so on. So I just transpose the matrix. Then I need to multiply the transpose to this matrix to anything different. So instead of a tedious process of finding the inverse of this 4x4 matrix, I just need to switch lines and columns in the rotation matrix. And I need to do one matrix multiplication, which is a lot easier than finding the inverse. And this allows me now to also, if I have some point P in 6, let's say it's a 6-dimensional coordinate plane, then I just make the P6, multiply it with a transformation matrix from 6 to 0, which is the inverse of 0 to 6. And I get a point representing in 0. I explain it so slow. Well, let's take a very special point in the plane, which is going to be the rest, the origin. So the P observed here is 0, 0, 0. If I observe the point in the rest plane, then the point is in the origin. And now I take this 0, 0, 0. I need to extend the homogeneous coordinate in the coordinate plane of the wrist. I assume it's a 6-dimensional, it's a 6 degrees of freedom robot. And I get here the rotation matrix, which rotates 6 to 0. I get the translation vector between the origins, which gets calculated exactly like this. Now expressed to the 0 plane. So if I apply sequence of this formation, I calculate in the end a vector which connects the base to the wrist. And I have 0, 0, 0, 1. What did I gain? Well, this thing is just the position of the wrist in the base plane. So this is exactly my forward kinematics. So if I multiply product of all contributing units from 0 to 6, and I look at the transformation from 6 to 0, the translation term gives me directly the position of my forward kinematics. This is exactly here on the next slide. You see that I have the position of my end effector encoded in the translation vector of this P6 to 0 matrix, and the orientation of my joint is still encoded in the rotation matrix, but I can now really multiply out now all the possible orientations of my robot, and I will see that if I want to represent the orientation of the anti-vector in a low pitch roll, so low pitch is basically the rotation around X, Y, and Z roll is around the Z axis pointing forwards. You see that we can group the elements the same way we were doing it earlier for Euler Angles, just using comparison between the elements and the products we have here from the PGO roll angles. We can recover the theta, C, and P, the yaw, pitch, and roll, just from sine expression from NZ, from inverse cosine of AZ divided by cosine P, and so on. So we can recover not only the forward kinematics in the translation, but we can also recover, in this case, for example, the yaw, pitch, roll representation directly from analyzing the matrix R of the translation vector. So we see that this allows us already to calculate for kinematics, but if you want as a manufacturer now to define to set parameters required to build the matrices to the user, you would need to specify 6 parameters for each transition. So from 1 to 3 translations, to go from 1 to 2, I would need to add another 6 parameters and so on. And the last part for today is to look at how can we simplify it just by constraining the selection. Let me just clean the board first. So we have our sequence of links, and now we try to understand how to specify the coordinate names. So what we can imagine, let's just do some Picasso. I have some sequence of links, specific figures, link. Let's assume we have rotational axis, so there is some rotational axis here. There is some rotational axis here. So this is the axis Z. And this is the axis Z I plus 1. This is the axis Z I minus 1. To train the number of ones we need to pass between between the manufacturer and the user, we use the dynamic parameter. And what do we say? The first parameter, the first definition is that the axis along which the actuator is performing its action is the z-axis. Z-axis is the axis is the axis of action. Because I see already people complaining a little in the EH lines. And the first one is choice of Z. Z-axis is the axis along which the action happens. If I have a rotational axis, this is my thumb rule. The thumb is showing basically the direction of the corresponding rotational vector. And this vector would be pointing out of the board. If the positive orientation would be in this direction, then the vector will be pointed. If I have a linear prismatic joint, then my axis Z would be pointing out of the board here. For a linear joint, the axis would be pointing. So first I choose the axis of motion. If I have a rotating vectors, there will be some rotation happening here, some rotation happening here, and some rotation happening here. The second in the vocabulary is the choice of x-axis. The x-axis, so this will be the x I minus 1, is the axis with depicting the shortest distance between the consecutive z's. So we see here the shortest line between two non-parallel lines is the line which is orthogonal above. And this will be so finding the shortest line of connection between the spatially rotated joints is the definition of x. The same is true here. This will be the xi. It's basically again the line between zi and zi plus 1. And once I have x and I have z, then I apply the right hand rule, the original definition of our coordinate, x this, z this, the y would be pointing into the board here, the same as here. So I choose these as the axis along which the anti-vector is that is acting as the shortest connection between consecutive axes. Well, there are special cases. What are the special cases? The first special case is, which is pretty common to the robot I'm drawing here. Look at the robot. This is the z-axis pointing out. This is a z-axis pointing out. I have two parallel axes in this case. For this special case, I'm really free in the choice where I place my x. But if my xi is at this point, usually I try to place it in such a way that I don't have offsets here to continue. So for parallel case, I'm doing the choice, but I'm trying to align it with previous or with consecutive x-axis in the system. What's the second case where the x-axis may not align? The second case is the z-axis intersect in one point, so the shortest distance would be 0. In this case, the x minus 1 is basically vi plus vi minus 1 normalized to 1. So I build a cross product of these two vectors, and this defines my x minus 1 maxis. Why is it the case? We will see in a moment. Just because, well, with these two, we defined already also the orientation of y. So now, what are my parameters? So when I travel from this orientation step to the next one, what do I need to do? I'm going from a minus 1. Let's move it back again, so people can read. Also the slide. Is I minus 1 distance. For the next one, for some joint I need to get some amount along the AI minus 1 axis, defined really by the shortest distance between these. What else is there need to do? The zi minus 1 and the zi axis may be rotated to each other, and the only rotation we have here, since I is orthogonal on both, a rotation around x by some angle alpha I minus 1. So alpha I minus 1 is the angle around which I need to rotate my coordinate plane to end up in the new one. So this brings, so now I travel from here to here and change my representation to the new version of the new coordinate plane. And now I need to go the distance between where the previous x intersects the z-axis and where the new origin of the next frame starts, down or up. This really defines if I go, this is the positive b direction, this will be the negative b direction, this will be some negative amount of b I need to travel here. And to end up in the new coordinate frame, I need to rotate on the angle theta I, which defines my current orientation of the joint. And these are 4 parameters from Denali-Kattenberg, which I need to define. And now you understand why the direction of the x minus I axis was chosen as a cross product of previous and the next z-axis. The lambda I is really the alpha I minus 1 is the vector of rotation around x to get from z I minus 1. So this will be my alpha I minus 1 vector. How much do I need to rotate around the previous x I minus 1 to get to the new z-axis? And well, this reduces the number of parameters you need to pass between systems to just 4. And from these, you can build on the transformation matrix just as a sequence. So depending on which way you go, here in this case, we translate around. So there is a if you go from here to here, what you're doing is you have translation x by a I minus 1 as a matrix. Then you have some transformation matrix which would represent only the rotation by alpha I minus 1 by some alpha I minus 1. This would be the next step, what's happening to the system. Then the next one is just a matrix which represents just the shift as in B. And the last one would be so, for example, a transformation matrix, which is representing only the pure shift along the x vector, is nothing else but an identity matrix for rotation. So the 3 by 3 matrix is an identity. And I get here a I minus 1, 0, 0. So this would be rotation. This would be this translation matrix. Translation matrix, for example, for rotation around x by an angle alpha. This would be because it's rotation around x. So the rotation matrix is one of the elementary rotation matrices we just discussed. So cosine alpha I minus 1 minus sine alpha I minus 1 sine alpha I minus 1 cosine alpha I minus 1. This is the rotational part. Rotation 0, 1. I will to you as an exercise, and you will also practice it for the last 3 matrices. So you get 4 such matrices, one like. And if you multiply them all together, you get transformation. Sorry, between this is the wrong one. You become a final transformation matrix for one link. So this would be the transformation between I minus 1 and I. Would be a result of these transformations, written as a matrix. This resulting 4x4 matrix, we still have a structure 0, 0, 1 on the bottom, rotational part, and you will see the 4 elements theta, d, alpha I minus 1, and alpha I, and a I minus 1 showing up in it. And now, what I want to do to find the kinematics of the robot is just the following. Let me just switch to the right slide. It's actually, I had this in my original lecture as something that was building up all the time. So you will see basically how each of these rotational z vectors, x vectors appear the shortest distances between axes. And in the end, what you get out of it is the table on the right, where the manufacturer can provide you directly with the values you need to use in the operation of the system. So you plug these values in the result of the multiplication, and you have directly the function to transform the wall frame and the wrist. And in the first tutorial I will post today, we will be practicing exactly this. We will be looking at 12 different robot structures and assigning pH parameters to them by defining the z coordinates first, find the axis, using the strategy of shortest connection, free choice. You see now why I put it aligned to the next one. This gives me a d equal to 0 in the table, and d equal to 0 actually makes this an identity matrix. So it simplifies basically the forms with many zeros in each table. And the second exception for finding the x-axis is if the two z-axes intersect. Then we need to do a vector product scale, and we have a free choice. This is always the problem in the exam. So you have a 50-50 chance to pick the direction. You can pick it out of the board or into the board. Both is correct, and we need to follow both solutions. And in the end, using the Berlin-Hartenberg, we reduced the number of parameters defining the changes between the previous frame and the next frame. We reduced them from 6 to 4, but this requires us to actually follow the rules defined by this. And you will see the application of this in the tutorial. Thank you very much for today. You don't need for the future, I don't think you will listen to all of it maybe at once. You can stop and start at any slide later. On the system will jump to the slide and will continue with explanation to the slide. So this helps you to stop and start again later. Thank you very much, and see you in the next lecture.